Greetings. This is Paul Jensen. I'm going to start the final chapter of this series, and it's titled UVC Dosing, Luminaire Selection, and Layout/Design. What we need to understand, as Dave Sliney talked about earlier, is the 8-hour threshold limit value. And when we're talking about threshold limit value, it's time weighted average, which means over 8 hours, the average, in this case, we're talking about irradiance of the eye for 222 nanometer wavelength can't be more than 5.6 microwatts per square centimeter. So if you measure, let's say 6 microwatts per square centimeter in a location, is that dangerous? No, but we want to check the space to see if there are quote unquote hotter spots, unquote. Why do I say that? Because a person most likely will not stand there or sit there, stare in the same direction for 8 hours continuous. If he or she does, she or he may not have a job the next day. Now, skin is kind of a different issue. Notice that for 222, the exposure limit is a little bit higher than for the eye. What does that mean? That means that the skin can be exposed to more UV than the eye and not have any adverse health effects. But if we're using 222 directly, we may get very low eye levels, but skin might be the controlling factor of whether or not we do anything. Meaning that we either move the person, move the fixture, if there's a significant irradiance level. Now, for the men who may not have a lot of hair on top, if they're sitting underneath a 222 fixture, that may not be so good if they're going to be working at their desk for 8 hours a day, and their irradiance level that's measured is 30 microwatts per square centimeter. So that's why it's critical to understand the meters, how to take measurements, and how to apply that information. When we talk about 254 for the eye, it's a much lower 8-hour exposure limit. So if somebody has a 254 louvered fixture and sits at their desk, stares at that fixture for 8 continuous hours, and the irradiance level at their eyes is 0.21 microwatts per square centimeter, then, yes, they might start to get some kind of irritation or photokeratitis. As we go higher to 270 nanometers, what do we see? An even lower TLV for the eye, but the same for the skin. So that means that essentially you can be exposed to half of the level of 270 light at 254. When we're talking about UVC dosing, there's several different parameters in which people use, and different methodologies that people use to come up with some kind of a minimum UVC dose in a room. There's volumetric based dosing strategies. And there we're dealing with, okay, what's the height of the physical ceiling? What's the height of the functional ceiling? We'll talk about functional ceiling in a minute. But it's important to understand, when to use which type of method, and not one is actually any better or any more precise than the others. Then there's the area-based dosing criterion, and we'll discuss that as well. And then the average fluence rate in the room. You can calculate it. There's some manipulations you can do to calculate ray length and whatnot to estimate the average fluence rate in a room. And fluence rate means irradiance from all directions. And it can also be modeled relatively easily, and we'll talk about that at the end also. And some people believe in getting as much UV as you can into the room but meet the American Council of Governmental Industrial Hygienists threshold limit value in the occupied space. So those are the four major criteria. We're talking about volumetric dosing. There are some data for a wavelength equal to 254, so that's low pressure mercury, that for M. tuberculosis, it takes about 12 milliwatts per cubic meter, or 0.343 milliwatts per cubic foot of UV to inactivate Mycobacterium tuberculosis. In the published study, the number was closer to 17. The unpublished study, which hopefully will get published in the near future, showed that with 2/3 of the dose we used in the higher exposure, we got essentially the same results. We don't know where that inflection point is on the curve, but we do know that with at least 12 milliwatts per cubic meter, we were getting the equivalent of 24 or more air changes per hour from the UV alone. Now, I said we talk about sealing some more, and I'm going to talk about physical versus functional sealing. Why the differentiation? Well, you may be in a room or a cafeteria or a gymnasium, or some kind of room that has architectural features. They may be sort of artsy so that you don't focus on the ceiling with all the pipes and wires and ventilation system and everything else. The other reason to differentiate is, above a certain height, there's a lot of dilution. So do we need to irradiate the whole upper part of the room, or do we only irradiate below architectural features in some given height above the floor? And when we take a look at airflow patterns, there's very little airflow in the upper part of very high ceilings. Generally, from where the ventilation ducts have grills or supply vents, from there down, you most likely have sufficient mixing to make UVC effective to inactivate microorganisms in the upper part of the room, and even with 222 in the occupied space. We need to irradiate space and ensure that there's adequate airflow patterns, meaning that air flows from potentially infectious people or from the occupied space to the irradiated zone and then back to the occupied space. Now, not all the organisms or viruses will be inactivated in one pass. It may take a few passes, but the idea is that there's continuous motion between the occupied space and the irradiated, which is an unoccupied space. Generally, when we're talking about functional sealing, we'll say it's about 10 feet. So if you have a room that has a 12-foot ceiling with no architectural features or anything else blocking, no ventilation, we talked about that before, blocking the UV, or in essence irradiating clean air coming into the room, then there's not much benefit to dosing that upper part of the high ceiling. So in general, we'll just default to a functional ceiling of 10 feet, or if you have architectural features that go below that, we'll use that lower ceiling. Or if your physical ceiling is below 10 feet, we'll use that ceiling. In some methodologies or some approaches, people, if the ceiling is actually less than 10 feet, they will dose it as if the ceiling were 10 feet. And why? And I mentioned it before, but in an 8-foot ceiling, you may have air supply in that upper part. You have your UVC upper room luminaire mounted 7 feet above the floor. So you're irradiating some of that clean air coming in, So you really need to put more UV into the room. So if instead of assuming an 8-foot ceiling, you assume a 10-foot ceiling, you'll put a little bit more UV, or roughly 25% more UV, into that room to make up for the irradiation of clean air coming into the room. I talked about another methodology called area-based dosing. And again, this is for a wavelength of 254 nanometers, and it's that same study for Mycobacterium tuberculosis. And in this case, for the lower UV dosing, if we dosed at approximately 31.5 milliwatts per square meter, or almost 3 milliwatts per square foot, what would we get? We'd probably get about the same effectiveness, which is greater than 24 air changes per hour, that we did with TB in the published study. Now, average fluence rate is kind of tough. In the study, we used a modeling program and estimated the fluence rate based on the modeling. Unless you take many measurements and taking a look at fluence rate, which is from all directions, it's nearly impossible to measure average fluence rate in any one point and then average it over the whole room. But from modeling, you can plug different fixtures into the model, put them on different walls, and then come up with an estimate for the average fluence rate of that particular layout. So what if we want to design for microorganisms less or more susceptible to UV than Mycobacterium tuberculosis? Well, if you're looking for an organism that's less susceptible than M. tuberculosis, what would you do? If it's less susceptible to UV, meaning it's more resistant, you definitely wouldn't want to lower the dosing any. If it's more resistant or more, if it's less susceptible or more resistant, then we want to essentially consider increasing the dose. We can increase it based on a Z or K value, and you learned about that earlier in I think it was Rolf talked about it and Dave talked about it. And you could do that if you have an organism that's more susceptible to UV, then would you lower it? I don't think so. Why not lower it? Well, you don't really want to lower it because next year there may be something more resistant. We've been through this COVID. We have some data on aerosolized COVID that shows that in one study it's much more susceptible to UV. Another study shows it's much more resistant than Mycobacterium tuberculosis. So what do? Well, I would just caution folks to use the dosing criteria for Mycobacterium tuberculosis, and if need be, raise the amount of UV in the room. And I would never go any lower than the basic guidance for TB. Now, I have the website link here. I'm not affiliated with Acuity Brands, but on their website, and also as a pull down from their software, and talk about the software in a minute, they have a lot of information on different microorganisms and viruses. And I just did one screenshot here. If we take a look under pathogen for SARS coronavirus 2, and the next column is reported dose required to inactivate 99.9% of the tested pathogens. And again, this is in laboratory conditions. And it gives it in terms of millijoules per square centimeter. So it's not a K value. It's the dose necessary to inactivate 99.9% of this particular pathogen or organism or virus. We're talking about coronavirus, so we're talking about virus. So under the column for 222, which is the excimer lamp, from one study where it's irradiating a dry surface in a petri dish, they came up with an estimate of 3.6 millijoules per square centimeter. When we take like 254, there are two studies, dry surface, came up with 3.4 to 4. So that's within the same range, which would indicate that SARS-CoV-2 is similar in susceptibility with pulse xenon, which sends out a lot of UV and other wavelengths. It takes a higher dose to inactivate 99.9. But again, these are all dry surface in a petri dish. Why is that important? Well, we're talking about irradiating microorganisms and viruses in the air. If we go down to this next row, this is human coronavirus. In a study for aerosols, it showed that it took about a third of the amount of UV wavelength of 222 to inactivate the aerosol versus the dried aliquot on a petri dish. So if we're taking a look at comparing organisms, we really want to do like with like. So if we're trying to do something with aerosols, which we are with upper room UV or whole room UV, then we need to take a look for data for aerosols, but not much data exists in the literature right now. This was off the International UV Association's website. They have a lot of nice documents on their website, but this document gives you fluence rate. If we take a look at this column in the middle where it says fluence UV dose in terms of millijoules per square centimeter for a given log reduction. So there's 1, 2, 3, up to 6 log reduction. And I have a CVF or colic virus feline, so it's a cat virus. But if we take a look here, for lamp type, these are low pressure mercury for 1 log inactivation, for 2, for 3, for 4, for 5. If we take a look at just this one row, okay, to go from 1 log to 2 log reduction, it takes 3 times as much UV. To go from 1 to 3 logs, it takes almost 5 times. To go from 1 to 4 logs, 6, and from 1 log to 5 logs, it's almost 8. So there's not a linear relationship, it's a logarithmic relationship of dose to inactivate based on the particular wavelength and the UV coming out. What we have here is a copy of a data sheet from a UV manufacturer. And you can see here it was tested by Intertech Cortland. It has 4 9-watt Philips lamps, so that's the UV source. And the total output of the fixture, and this is needed for dosing, right, is almost 300 milliwatts or 0.3 watts. So if you're doing a layout, and you would do a couple quick calculations in a moment, but if you do a layout and say, okay, I need 1 watt of UV in this room, and let's say this is the only fixture available for you, How many fixtures do you need? Well, 3 would be 0.9 watts. 4 would be 1.2 watts. So we have to go back to our risk assessment. Is this a high risk area? Is it supplemental to ventilation? Is it supplemental to natural ventilation? Are there times when this is the only means of disinfection or inactivation of organisms or in the air? There's no true removal. There's not a room air cleaner, or it's not a very effective room air cleaner. Well, what you might do for a higher risk setting is round up. So you might need 4 in this large area or waiting room. And if it's a relatively low risk area, let's say it's cubes in offices and stuff, and there's not much transmission of anything there, then you might do the layout with just 3 of the fixtures. And when we talk about layout, we have to understand, okay, where will we put these? Is there a pillar in the way or a beam in the way that would stop the UV from being effective? Is there a way to get the maximum ray length or maximum both in the X direction and the Y direction spread of the UV iso irradiance lines? So within a facility, you may say, okay, on paper it looks like, oh, we'll put it on this wall, and this wall. In reality, when you actually look at the space, the one wall you thought we were going to use is really an all glass wall, and you can't exactly drill through the glass to install a UVC source or UVC luminaire. So you have to go back to literally the drawing board and say, okay, where can I put it? And it'd be a compromise to some extent. Then we have to make sure that, okay, can we get electricity to that lamp? And if so, how? Is there a way to switch the lamps off when you're doing maintenance? So there's lots of things that go into the thought process. And here we talk about the draft GPC, which is Guideline Project Committee. Number 37 is developing some guidelines for application of upper room UVGI. Now I talked about lighting simulation, lighting software. Signify and Philips have a program called Relux. It's this center one here. And Relux, you can go into these 2 links, but Relux is relatively simple to use, but it's a simple program. It doesn't have quite the diversity of the next one I'm going to talk about. Or, this one you can place fixtures, assuming you have an IES file, which means that the fixture is tested and we know roughly what the shape of the iso irradiance lines are of that fixture. And from that, what we do is we input it. We can put it on wall A, wall B, move it part way through. We can stagger fixtures. We can angle them up. We can angle them down. And what these software programs will do is give you, and that's the important thing, the average fluence rate in the room. If you move a fixture on a wall, you may find, okay, I'm losing 20% average fluence rate in the room. So maybe that moving it in that one direction was not so good. But that's the only thing you can do, so you have to live with it. Otherwise, find another spot. The other program is by Acuity Brands, and it's called Visual. Visual has also been around for a long time. Both of these were originally lighting programs, and they added on a module for ultraviolet. And the Visual, I have more experience with Visual than the other, so I'm going to speak about Visual a little bit. But there you can pick organisms, you can pick a height above the floor in which you want to find out what the your radiance or fluence rate is on different points. You can do the same thing about moving fixtures around. You can change reflectance of walls. You can change the height of the ceiling. You can move it down to some functional ceiling level and see what you get. So it's pretty rigorous program to play with. You can also pick an organism if you want to pick an organism. You can get equivalent air changes per hour. Again, that sort of is stretching it a little bit, but I do think that from the standpoint of design, something like visual is a nice tool. I wouldn't design and I'm using name brand, but a Boeing 777 using visual, though with a high-tech modeling program, they did a lot of the design work on a computer. But again, for UV and the uncertainty in the dosing values, we would just use it more as an advisory as opposed to an absolute. During the course we did last August, Mike Kruger from Acuity Brands showed us some software. We did some calculations. So what I'd like to do now is take a look at a couple different rooms. Mike also had these dimensions in his on his computer, so he could punch it in and we could compare values. And we compared dosing based on area, based on room volume, and based on average fluence rate in the room. We also had him pick a level that was roughly 6 feet above the floor and find out what is the maximum irradiance or fluence rate at that height above the floor. So get your pencils out. Let's have a small room with dimensions that are 3 meters by 5 meters by 2.7 meters. So what's the volume of the room? The volume of the room is 3 times 5 times 2.7. What's the area of the room? 3 times 5. What do we have for dosing criteria? In your presentation handout, you should see, okay, for volume, we talked about 12.1 milliwatts per cubic meter. So what level of or amount of UV do we want in the room as a starting point? It'd be 3 times 5 times 2.7. That would be the minimum times 12.1 milliwatts per cubic meter. Now let's do the area dosing. So the area dosing we know is 31.5 milliwatts per square meter. What's the area of this room? 3 meters times 5 meters, or 15. And we multiply that by 31.5 milliwatts per square meter. Now, we don't get the exact same answer, do we? No, and that's because when we're talking about dosing criteria, there are very few data. So we want to take a look and see, okay, if it's a high risk area, we might go to the higher value. If it's a low risk area, we might go to the lower value. And when we take a look at the output from visual, which we don't have the luxury of having right now, we would probably see that with that type of a setup, we could pick what fixture we want that would be close to the amount of UV needed in the room. And then what Mike would do is he put it on the short wall, then put it on the long wall, and we would compare the average fluence rate in the room. And we would see, okay, if we put the UVC fixture, and we're talking 254 at the moment, on the long wall, and we assume 10% reflectance, what we might find is that we have about 4 or so microwatts per square centimeter fluence rate, or average irradiance from all directions. Now, if we put it on the short wall, we might gain 10%. And in this case, this example, we did gain 10%. So putting it on the short wall allowed that UV isoirradiance line, the isoirradiance line to go, out further before it hit a wall, and then most of it being absorbed, which meant that on the short wall, you end up with more photons or more UV in the room. Now, if you have a corridor, what do? Well, you just have to put luminaires in there that aren't putting out iso-plus or isoirradiance lines way out to the side. You want something that's semi-focused to go up and down the corridor. We also, after this, we did an example of a very large conference room. And what we'd like to do for the course, and that's why I need the PowerPoint for the different rooms and dimensions, we're going to pick a couple of the rooms in the, that we use in the classroom and use those in the exam. So, from that, what you'll need to do for the exam is calculate, okay, how much UV do we need? We'll give you a certain number of fixtures, types of fixtures, and then we want you to estimate how many of which fixture and where you might put those fixtures. Now, if we're talking about 222, we would do a very similar thing, though we don't have dosing data other than laboratory. We don't have human dosing data like we do for TB. But if we assume similar requirements, then what would happen? We would need less 222 total in the room. So you can expose people to a higher level, irradiate above or at a higher level than you could with 254. And the benefit of the 222 is you're inactivating organisms in the occupied zone, maybe the upper part of the occupied zone, plus in the upper room. So you get the benefit of upper room UVC, and you get the benefit of some UVC in the occupied space. But as we talked before, if I'm 30 centimeters from you talking or coughing or sneezing, even the best ventilation or the best designed UVC system or a combination of 254 and 222 would be of little benefit or protective value when we're in close proximity to each other. But once you get a certain distance away, we know from many studies that the large droplets will settle relatively quickly. Yes, the small ones will move around, and with airflow currents, they'll move slowly, and there's potential, especially with the 222, of inactivating some of those organisms before it gets to the person that's, let's say, a meter and a half, 2 meters away. So that's it for the layout and design. If you have any certification questions, please contact Eric, and I thank you for your time.